on what we're doing here. We have to make sure we get through all the rest of the notes today, okay? Because tomorrow is supposed to be review day, all right? And I want to give you maximum review time in class because we have such little time tomorrow, okay? So what we're going to do is still try to cover as much as we can, right? I think we'll be able to get through most of it here. Mr. Goff said we could skip example 9. I might come back to it at the end if we have time, hopefully. Anywho, we left off here at letter C, okay? So I guess one thing I will kind of talk about just briefly here with letter B, okay, because this is one we kind of like sat on for like a good, I don't know, 10, 15 minutes, maybe more than that, but anyway, what I want to talk about there is kind of what I talked about right here with Christian earlier in the homework, right? Where if I use different colors, it's maybe easier to see how that region is changing there, right? And so, I'm gonna just really quickly redraw this example here for letter B, just so you can kind of see what's going on, okay? And so we had, what was it? It was 3 cosine theta, so I don't know, 1, 2, 3. And so let's see if I can make this 3. So 1/2. I don't know if that's gonna look okay. We'll see. Something like that. And then also 1 plus the cosine of theta, so like 2, and then 1 negative 1. Okay. So 2, 1. No, I got it. There, negative 1, and then back there. So something like this. Okay. And then the region was the common interior. The common interior there for that. Okay. So it involves kind of like okay. So again here for that common interior, right? Remember that we're always kind of like calculating that interior out from the pole. That's why I like to kind of draw, rather than just shading it in like willy-nilly kind of thing, I like to kind of like radiate out from the pole because that's what we're using there. We're using these little wedges, okay, to kind of like fill in that area, stuff like that. And so hopefully now it's maybe a little bit more clear, right, about why we have to kind of use 2 integrals, because our outermost curve changes, right? Starting at the state equals 0 here, right? And as we rotate around, you can see that we have the red curve, red curve, red curve, red curve for the outer boundary. And then at this point, which we don't know, all right, but we can figure it out, right? Or we didn't know, we figured it out. At this point, right, now our outermost boundary is the blue curve, which is that the 3 cosine, okay? And so we need to then write 2 intervals. One where our outermost boundary is from this theta angled up to this theta, and then one for where we start at this theta and then close on down to that. Well, that's going to be the pi over 2 there when you get to that. Okay. So I don't know if that makes it more clear or not. My graph isn't super great, so you don't see the symmetry there, but it is there, kind of thing. Okay. So I don't know if that helps or not, but I mean, and maybe I'm just doing something silly by revisiting an old problem that we already spent 20 minutes on, and maybe you all get it now, but I don't know. So. Are there any, does this help at all, or is there any questions on this? I mean, maybe it doesn't help. Maybe I should just move on. But all right, we'll just move on then, all right? Because we'll see another one just like this in just a little bit. So we finished letter C, but not quite. We had a second question here, okay? We were asked to then determine at what rate the distance between the 2 functions is changing when theta equals 2 pi over 3, okay? So if we want to find the distance between the 2 functions, what would be an expression that we could set up here to find the distance between those 2 functions? So you're jumping ahead of me, but yes, we will do a drd theta. I'm just asking. So I don't want the rate of change. What will be an expression? Because, well, actually, maybe that's a good point to start from right there. We do want to find a drd theta, right? But we want to find the rate of change of the distance between the two functions. So in other words, we have to first come up with an expression for the distance between the two functions. Then we can take the derivative to find that rate of change of it, right? So again, back to my original question there, right? What would be an expression we could use to represent the distance between the two functions, and specifically at theta equals 2 pi over 3. So if you can look here, right, 2 pi over 3 would be like this angle right here. So what would be an expression we could use to describe the distance between the two functions along that theta there? Well, if we go back to our picture we had before, when we talk about area between two curves, how can we describe the distance between these two functions at this point, for example, right here? What would you do? What? Yeah, top curve minus bottom curve. F, the value at F, subtract the value at G, right? That would be the distance between those two curves. So for polar, right, we don't do top minus bottom, we do outer minus inner, right? And so at 2 pi over 3, what is the outer curve? Yeah, it's those two, right? It's that R2, right? And then the inner one is 2 minus 2 sine theta. So then the distance, okay, is 2 minus, sorry, thanks. I'll zoom out some, I guess. There we go. The distance is going to be 2 minus the quantity, 2 minus 2 sine theta. Okay, just like that. That's your distance. Or if we simplify, right, the 2's will cancel, and with a positive 2 sine of theta. But again, we're not interested in the distance at 2 pi over 3. We're interested in the rate of change of the distance at 2 pi over 3. So now what should we do? Take the derivative, right? So I'll take the derivative. I'm going to do, I don't know, the derivative with respect, I don't know, I'll do it this way. The derivative with respect to theta of 2 sine of theta. Okay? Which is, what's the derivative of sine? So yeah, 2 cosine theta. Okay, so that describes the rate of change of the distance between those two functions, all right, at any theta, but of course we want it at specifically 2 pi over 3. Okay, and so 2 cosine of 2 pi over 3, well, that equals -1. Well, cosine of 2 pi over 3 is -1/2, but then times 2 gives you the -1 there. Mm-hmm. So that is the answer, right? We don't need to proceed on from there, but what does that tell us? A negative derivative, a negative rate of change, what does that tell us about the original function, the distance there? It is what? Decreasing. Does that make sense here, right? If you look between these, at 2 pi over 3, right, is the distance decreasing between these two functions? Yeah, you can see here, right, that inner curve is kind of like bowing out, right? It's extending out a little bit, and so the distance between those two is, in fact, shrinking. Right? So that makes sense. Right? As you would kind of rotate around here from 2 pi over 3 on around, the distance is shrinking. All right, questions on any of that? All right, so guys, go ahead, graph letter D and see what you can do there. All right, I'm going to have you guys go ahead and just tackle this one. All right, there's no new surprises here. There's no new surprises here. So, say again? We will see. We will see. We're probably going to skip it and then come back to it if we have time at the end. Okay. Skip it and come back to it if we have time at the end. If you did it or something like that, or you do it on your own in the meantime, kind of thing, I'll be able to, of course, show it to you or something if you're interested. But I want to make sure that we get through the, example 10, and then also arc length. But luckily, arc length isn't awful. So. Well, I mean, if you like the other arc lengths, you'll get this arc length pretty easy. Okay, I guess I will do the same while you guys are. So, can you guys tell the difference between blue and green there, or should I use more contrasting colors? Or how about like this? Maybe I'll use let me see if I can use, like red really, so like maybe like red and blue maybe? Does that sound good? All right. Be patriotic. Red, white, and blue. And some black, too. But. All right, so. Yeah, whatever. Bless you. Okay, so. And again, try to use symmetry if you can here. Okay. Yes. Which one are you doing for which one? 3 cosine theta. Yeah, it should be just more like this. Or it should be more like this. So let's see here. 0 will be 3, pi over 2 will be 0. That's right. Pi. So pi will be a negative 3. So in other words, pi is negative 3. You're going to go 3 in the direction. You're going to be the other direction. Yeah. Question? Yes.
For this side, how do you like just look at that and know whether it's gonna be curved around or whether it's gonna be like?
So think about, you always want to think about going to 0 and you want to go turn counterclockwise around as you go. So it's going to have to go to here, and you got to go to this. And you just kind of like rotate out to it. You're going from an R value. Circle-y, I would say, yeah, because that's only an R2, that's an R3, so it's not going to be circle, you know, the radius is the same, so it would extend out. Okay, so I'm going to zoom in here on just the graph first. Okay, the important stuff there. Okay, so again, it's the common interior, or well, it doesn't say common interior, it says the region enclosed by these two curves, but it's going to be, you know, kind of like, oh, maybe I shouldn't use red. I'll use black. Okay. So if we use symmetry here, how many integrals do we need to write? 2. Very good. Okay, our outer curve is changing again. If you look, I'm going to do it up on here on the screen so that way people at home can also follow along. If you look here, right, if we start at 0, right, we got the blue curve as our outermost curve, but then as we continue rotating around, the red curve becomes our outer curve there as we kind of accumulate the rest of that area there. Okay? So the question is, right, where are we switching? At what theta value do we switch from that blue curve to the red curve, right? From 2 minus cosine theta to the 3 cosine theta. Where do we do that? Well, to find out where they intersect, you set them equal to each other and solve, and you get theta equals pi over 3 and 5 pi over 3. This angle is going to be the pi over 3, right? We're in the first quadrant there, so that's pi over 3. This angle down here will be the 5 pi over 3, the other point of intersection right there. Okay? So then we integrate from 0 to pi over 3, this blue curve being our outer radius, right? And then we integrate from that pi over 3, and then from pi over 3 to what for the second integral?
0.
Well, right, it's when r goes to 0, and how do we know when r goes to 0? It's pi over 2. And again, if you want to check that, you can always check that by setting that r, you know, the red curve there, 3 cosine theta. You can set that equal to 0 if you need to, and of course then that's when pi over 2. Or 3 pi over 2. And of course we want the 3 pi over 2 one because that's kind of where we are right there in the graph, right? So there's our answer using symmetry. Okay? Yes, question?
So how accurate, like, do our graphs have to be?
How accurate they have to be? Well, it depends. If the purpose of the graph is just to help you out with setting up the integral, then they can be as inaccurate as you need them. I mean, as inaccurate as you want. You know, I mean, just so they can help you out. So obviously, your goal should be to graph them accurately to help you out with the, you know, the analysis and stuff like that. But I don't think there's anywhere we necessarily grade you. I don't think we're gonna like necessarily grade you on how well you graph. It might be. If the question asks you to graph the polar function, then you're going to get a grade for it. You want to be as accurate as you can with that, of course. But then with your own graphs. So again, I recommend bare minimum you get the 0, the pi over 2, the pi, the 3 pi over 2s. Okay, if you can't figure it out from there, then try to get additional points. But really, you should be able to get most of the graphs with just those 4 points. Okay. All right. Any other questions on this? All right.
For these ones, why isn't there any subtraction involved? Like,
Why is there any subtraction involved? Okay, so good question, right? Let's go back to what we talked about. Back to stuff that's more familiar, right? Back to rectangular coordinates, right? When we subtracted these. Why did we subtract these curves here? Well, because we have some kind of like white space, some white area we want to remove from our area calculations. You see that? Like we're integrating from the x-axis. This is kind of like our 0 here. And so we're accumulating all this area. So we're going to take the function f, which counts all of the area under f, right? And we're going to take the function g, which counts all the area under g. Take that area under f, subtract off the area under g, and that leaves then what remains between the two functions. So we subtract in that case because there's an outer thing and an inner thing we have to subtract out because there's like there's an empty space between. Okay? What we've got in this scenario is more like, and I didn't show this yesterday, but I'm going to show it to you right now. What we have in this scenario is more like when we have a function that goes like this, and maybe like a function that goes like this. And you're trying to integrate again from a to b here. This is f, we'll say this is g. Our situation here is that the top curve changes right at this point, so we have to set up two different integrals. One from here to here, one from here to here.
okay.
Because the
And
top
there's no,
curve
like,
changes.
space.
Exactly, there's no space, it's still the same thing. Does that make sense? So equivalent to that here, if you can like look at it. So let's compare that to like here, for example, right? Here, in this problem, we did subtract. Why? Because we have kind of an inner thing we're getting rid of and an outer thing we want to hold on to. Like we want to get the area between the two things. Does that make sense? So Gabe, I'll be right with you one sec. But here, right, you'll notice there's from our R, like if we radiate out, there's no white space between our region and the R. So it's just the fact that the curves are changing, the outer curve is changing. Okay? That's the idea. Yes, Gabe.
I tried to do like the first one you showed where I guess there was like an inner circle inside another circle on the previous page. Does that still not apply here?
You're saying like here?
Or
Here?
Yeah.
So this one was also,
I meant previous one back. The most simple one. I thought
this one right here.
yeah.
Okay, what about it?
Could you not apply the same thing? Because I did integral 1/2 0 to pi over 2 of 3 cosine squared 3 theta minus 2 minus cosine squared.
You're saying for this one right here.
Yeah. Can you not do that? Because I try to integrate, I guess, the entirety of the.
You trying to integrate the blue one?
I was trying to integrate the red one, I guess, and then
Okay.
subtract the.
So again, integrating the red one would get you, so let's just, so, and your limits of integration were from 0 to pi over 2, you said?
Yeah. And then
So-
multiply by 2.
So let's think about, and then multiply that by 2. Okay, so again, you'd be including this space then, too. This space as well. If you integrate from here, it would go out for the whole thing. Your upper curve would include that as well. And then you subtract out this little, like, you'd be subtracting out the curve. You subtract out this little space, but then yeah.
You're not subtracting.
Yeah. So you see what I'm saying? So it doesn't quite work with what we're trying to do there. Does that make sense now? Okay. So anyway, we'll skip example 9 then. All right. All right. Any other questions before we move on? Want to make sure we're okay. All right. We're skipping example 9 for right now. We'll come back to it. I promise. Well, maybe not. Tomorrow, maybe, if you guys really want to see it, I'll be happy to go over it too. Or if we have time at the end. Mike says you don't have to. Well, that's really generous of you, Mike. Thank you. All right. So anyway, you can see here this graph didn't quite complete, so I'm just going to kind of complete it for us right here. Okay, this is calculator active though, so you also could have just like kind of seen it in your graphing calculator. Very strange polar curve we've got there, but there it is. Kind of looks like a profile of a bird or something like that, bird's head or something like that. Anyway. The curve shown below is drawn in the xy plane and is described by the equation in polar coordinates theta plus sine of 2 theta. Only for 0 less than or equal to theta less than or equal to pi. Okay, so that's a unique, normally we go from 0 to 2 pi. It's only from 0 to pi here. R is measured in meters and theta is measured in radians. The derivative of R with respect to theta is given by, so we also give us the derivative. That's nice of them. All right. So, letter A says, find the area bounded by the curve and the x-axis. So go ahead, set up your equation there. Okay, do it. This is calculator active too, so feel free once you have it set up to go ahead and type this in your calculator and you can get an answer as well.
So because it gives us R, we have to change it to.
In terms of x and y and stuff like that. So, I mean, we're trying to find the area under this polar curve, and so we want to keep it in terms of r and theta. We don't want to change it to x and y. Now, later, that might change depending on the kinds of questions we're asking, but for right now, we're just going to keep it in terms of, yeah. So remember, you only want to graph from 0 to pi. Do you know how to make it sure graph? So hit the window button, because this is a matter of the window. You'll see theta min, theta max. So what's your theta min you want to do? There you go. There you go. find a value theta. So you're trying to find that angle, right? That corresponds to the point on this curve in the first quadrant, because obviously that's where it's first, the origin. So greatest distance from the origin. Well, what describes the distance of this thing from the origin? It's the r, right? It's the r. So this curve is what describes the distance from the origin, right? So you don't have to do anything special with that. But we're trying to find the greatest distance. So in calculus, we want to find the greatest of something. What do we do with it? Take the derivative of it. And then what do we do to find the maximum? Once you have the derivative, what do you use? What do you do then? The maximum using the derivative. What do you do with that? Right? Say again, set equal to 0, get your critical points. Right? And now, is this an absolute maximum we're trying to find or a relative maximum we're trying to find? It's an absolute. So you may also want to include the endpoints of your interval.
Oh, with the x coordinates.
And you evaluate those critical points and the endpoints back in original function, right? Because that's describing the distance, and that'll help you find the distance. All right, so we got letter A. Maybe yes, we're good. Moving on. Okay, any questions on letter A? All right, maybe you moved on to letter B, hopefully, maybe. Okay, so letter B here, right? Find the angle theta that corresponds to the point of the curve with x-coordinate -2. Okay, so we have to take a theta and somehow get it to relate to an x-coordinate of -2. How do we relate x and theta? What do we have that relates those? X equals r cosine theta. Exactly right. Okay? But this is x in terms of r and theta. We need to get just x in terms of just theta potentially here, right? But what is r in our situation here?
Theta plus sine.
Exactly. Theta plus sine 2 thine. Theta plus sine of 2 theta. 2 thine theta. Sometimes I get my merds mixed up. Okay. So we'll substitute in for the theta plus 2 sine theta. And now just, what should we do here? What is x? -2. Okay. Right. And so then, how do we solve this equation? Use your calculator. Exactly right. Don't even bother trying to solve this equation. Use your calculator. What mode should we be in to solve this equation? I would say rectangular mode. I mean, I think you might be able to do this with polar, but I would suggest using rectangular. Why? Because rectangular, when you go to second trace using the calculate menu, you can use the intersect command. In polar, you don't have an intersect. So if you graph this and graph this, you won't be able to, use the intersect command there. So we're going to go back to function notation here and just solve the equation that way. Okay, I already have it done there from, I guess, yesterday when I was doing it. Okay. And of course, we want to be careful here because you can see that my -2 intersects more than one spot, but we want to keep our theta where? Theta has to be between what? 0 and pi. So you want to make sure that you choose, and what might be helpful here is to adjust your window to guarantee that you're only considering those theta values between 0 and pi. So now when I graph, you'll see the curve. And there's only one location where that -2 goes through. Okay, and so we get 2.7860609. Ugh. Okay. So there's our answer right there. Sorry, yeah, function, which is rectangular. Yeah. Okay. All right. Letter C. For pi over 3 less than theta less than 2 pi over 3, dr d theta is negative. Okay? Which means if dr d theta is negative, what does that tell us about r? Say again? Okay, so yes, that means, so it tells us really two things, I'll say. So that's more talking about the curve, I would say. But what does that say about r? If dr d theta is negative, r is what?
Decreasing.
Decreasing, yeah, decreasing, okay? So the radius r is decreasing for pi over 3 less than theta. It's important to mention that interval because, if you just say the radius r is decreasing, well, okay, that's true for some of it, but maybe not for the whole thing. And so you want to make sure you indicate the interval there. For pi over 3 less than theta less than 2 pi over 3, since dr d theta is less than 0 on that interval. Okay, and then, right, Will answered the second part there. What does this fact say about the curve? So if our radius is decreasing, that means the curve is doing what? Getting closer or getting smaller, getting closer to the pole, I would say. Okay, now I'm going to throw in an extra little piece here because I think this is important, right? If r is decreasing, well, if r is negative and decreasing, that means it's getting further from the pole, right? But since r is positive here, okay, for pi over 3 less than theta less than 2 pi over 3, then the curve is getting closer to the pole. Right. If you're already starting with a negative, so if we had a negative radius, and the radius rate of change was negative as well, that would be a decreasingly, negative. So it'd be more and more negative. You're actually getting further from the pole here. But since we have a positive radius and it's decreasing, that means it's getting close to that pole of 0, right? Radius of 0. All right, last one here. Find the value of theta in the interval from 0 less than or equal to theta less than or equal to pi over 2 that corresponds to the point on the curve in the first quadrant with greatest distance. So first of all, we're looking for a value of theta, so we're looking for an angle, and that results in the greatest distance from the origin. Okay, so greatest distance, that is what kind of, Gabe, you have a question?
Yeah, how did you know r was positive in the previous one?
I'll come back to that. Let me just finish this real quick. So what concept do we use to find greatest something in calculus? Yeah. So in fact, not relative max, absolute max. How do we find the absolute maximum of something? What do we normally do? Use the critical values, which is when the derivative of that thing is equal to 0 or undefined, right? And also including the endpoints as well, and we evaluate those things, okay? Well, we're trying to find the greatest distance. What thing here is describing the distance from the pole, or the distance from the origin? R is exactly right. And so it is R that we're trying to find the greatest value for. So then we'll take the derivative, which you already have, dr d theta is 1 plus 2 cosine of 2 theta. I'm not sure why they give us the derivative here. That's a very easy derivative to take. My guess is maybe they felt that this was going to be too tight of a problem, and so they give it to you to help out. But, I mean, again, the derivative is pretty quick to take. So anyway, we set this thing equal to 0, right? Cosine's never undefined, so we don't have to worry about that. And so you get cosine of 2 theta equals negative 1/2. Okay, now I know this can cause some people some trouble here when you have that 2 theta inside. But imagine this is just saying cosine of something equals negative 1/2, right? What's the something that would go in here that would give us a negative 1/2 when you take the cosine of it?
2 pi over 3.
Right, so 2 pi over 3, and also 4 pi over 3, but I guess we can throw the 4 pi over, well, actually, no, we want to hold on to that, never mind, for right now. Sorry, so 2 theta, right, is this thing that's inside the parentheses there, and so it's 2 theta then that equals 2 pi over 3 and 4 pi over 3. If we want just theta, we have to continue dividing by 2, and so we get 2 pi over 6 and 4 pi over 6, which simplifies to just pi over 3 and 2 pi over 3. Okay? So should we consider both pi over 3 and 2 pi over 3 there as critical points?
No.
No, why not? They're equal to 0. One's out of the interval. So we want to throw out that 2 pi over 3. Exactly right. Okay. And so we've got our critical point. So is our answer pi over 3 then? But that's the only answer I got. We have to also check 0 and pi over 2 because those are the endpoints of our interval. Remember, that's how you find absolute maxes. And we check them by doing what with them? plug them. You can use a number line. Actually, in this case, that would be okay. But I'm going to suggest this. Let's just plug them back in for r here, okay? So I'm going to do theta and then r. Just do a little table. And so we'll say 0. We'll say pi over 3. We'll say pi over 2. Okay? And so then theta equals 0. R, which is equal to theta plus sine of 2 theta. R would also be 0. Okay? For pi over 3, I'm going to use a calculator to do this. All right, so pi over 3 plus sine of 2 times pi over 3. I get about 1.913. 222. I'm not going to do a million things there. And then we'll do pi over 2. So pi over 2 plus sine of 2 times pi over 2, which is 1.57. 0.796,327. Okay? So what's our answer here? Pi over 3. Again, the answer was the value of theta that corresponds to the point on the curve that's the greatest distance from the origin. So it's theta equals pi over 3. Okay. The justification is our work here. This table that shows we considered both the endpoints evaluated in the function and the critical point evaluated in the function. Right? Also showing the derivative equal to 0 there. Very important too, right, for the critical point calculation. Okay. Questions on that? All right, so let's review arc length. So here we go. All right, rectangular is the integral from a to b, right, of the square root of 1. I'm going to put the dx over dx here just for our purposes, but then I'll show the, and then plus dy dx, quantity squared, right, and then dx. But of course, right, we know that simplifies to a to b of the square root of 1 plus really just f prime of x squared, right, dx, like that. Okay. All right, so that's review, right? We've known that one. What about parametric? How does that change for parametric equations? So the first one's going to be dx dt now, right? Because we're no longer taking the derivative with respect to x. We're now taking the derivative with respect to t, the parameter, with respect to the parameter, because that parameter is now our independent variable, right, as opposed to the x. And so then dy dt will be also the other piece there. And we're going to integrate with respect to t, right? Okay, so actually I don't need to simplify that one at all. And then for polar, well, this is a new one, right? We haven't talked about this one. Well, the integral will still be from a to b. There's no change there, okay? There's no coefficient in front or anything like that. It's still going to be the square root. Anyone want to take a guess about what the first piece is going to be? Dx d theta. Exactly right. Okay? It's exactly the same. It's exactly the same as the parametric because we're just swapping parameters. Our parameter in parametric is t. Our parameter in polar is theta. And that's all that really happens there. Okay? There is a way to simplify this down. There is another arc length formula here for polar. If you want to learn one more formula, okay, you can feel free to identify that one, or I can look it up for you. I forgot what it is off the top of my head, but it does kind of simplify down. My thinking is, these are so closely related. Why not just, learn these three right here rather than learn a whole other formula that's, more simplified or whatever. So, your choice. But anyway, example 11, let's go through this here. And again, we're just going to set these up. We're going to say these are just calculator active. We're going to set them up. This one you can actually do by hand. It's not awful, but again, I'll be happy to show it by hand if you want to see it later or something like that, if we have time. So we're finding the length, which means arc length, of course, of the spiral. R equals e to the theta. So if you graph that, right, that means you're just going to spiral out from the pole there and create this, spiral, I guess, anyway. And we're given the limits of integration. That's really nice. From theta equals 0 to theta equals pi over 2. So I'm going to write down the arc length formula here. A to b square root dx d theta squared plus dy d theta squared d theta, like that. Okay. So now we've got to come up with dx d theta dy d theta. And all we have is r equals e to the theta. We need to come up with a function that's x, that has x in it, right? So again, how do we relate? What is x in polar coordinates? R cosine theta. So x is going to be r, but we know r is e to the theta, and then cosine theta. Okay? And then what will y be?
E to the theta sine.
E to the theta sine theta. So again, what we're really doing here, right, this is a parametric equation. We're writing x in terms of a parameter. We're writing y in terms of a parameter, okay? We've taken our polar, we've rewritten in terms of a parametric equation, and now we're just going to essentially use parametric arc length formula, right? We're going to take the derivative of this with respect to its parameter squared, plus the derivative of this with respect to its parameter squared as well, right? And then square root the sum. So we're going to take the derivative here. The derivative of x here with respect to theta, we're going to have to use what? Product rule. Okay, so we end up with e to the theta cosine theta minus e to the theta sine theta. Okay, here dy d theta, again another product rule, e to the theta sine theta plus e to the theta cosine theta. Okay, just like that. Oh, wow, push me a little bit there. So now let's actually set up the arc length here with those derivatives, right? So the integral will be from 0 to pi over 2. Limits of integration are given to us, thankfully. All right, square root of dx d theta, which is that right there. So e to the theta cosine theta minus e to the theta sine of theta squared plus e to the theta sine of theta e to the theta cosine of theta squared, square root that whole mess there. Believe it or not, this can be done by hand. Okay, it does work. It's not awful.
Shit.
When you end up foiling this out and foiling out the other one, things will cancel. You'll be able to factor out an e, and you'll end up with actually a Pythagorean identity of cosine squared plus sine squared. It ends up just being in terms of e at the end. So it doesn't work too terrible. And again, I'll be happy to show it to you guys if you want later or something like that. But for right now, I will also say, let's type this into our calculators. Okay, because we need to be able to evaluate this. Yes, let's do this. Now, let me make a suggestion. Rather than trying to type this whole mess, right, into your calculator, first of all, what mode do we need to be in for this?
Function.
It could just be function if you wanted to. Exactly right. You don't need to use, polar just because that gives you a theta variable. This is, at this point we can just use the function mode. If you want to use, whatever method you want to use there is fine. My recommendation though is to take your dx d theta, put that in your y equals here. So I'll put e to the x cosine x minus e to the x sine x. We'll do the same thing then for our dy d theta as well. E to the x sine x plus e to the x cosine x. So put the dx d theta in y1, dy d theta in y2. And then when you go to your home screen and you do math 9, we'll go integral from 0 to pi over 2. We'll type the square root there. And then we'll do vars, right, the vars button. And then arrow over to y vars. I type this in y1, so I have to use the function. If you type this into like r1 and r2, you would want to go down to polar and then use r1 and r2 there. But since we used function, I'm going to use function y1, and I can hit the square button and square it, plus vars y vars function y2 and square it with respect to x, and we should get something like 5.388828791.
Yes.
Okay, good.
No.
No? Yeah, don't forget the squares. But I just think this makes it a little bit more palatable when you can kind of like break it down into the pieces, and then you don't have to because your screen just can't hold all that information on it, and so it's hard to kind of make sure you're typing everything in correctly. Okay, so we're all good on that?
Yep.
All right, so again, use that if you'd like, or forget it if you don't. Okay, that's just a little tip. All right, so now we want to do number 12 here.
Oh my god, this is bad.
I know, right? How can you be so lucky today, Mike? We're gonna do it, Mike. We can make it. I
I don't
believe in
think so.
us.
I can.
Okay, well, we'll leave some people behind, I guess, but. All right, find the length of the graph of 3 cosine theta. Okay, okay. So 3 cosine theta looks something like this and like this. Ugh. Okay. We're not told limits of integration here, but what are limits of integration going to be? Yes, 0 to pi. How'd you know? Took a guess? Okay, well, where does our curve start? Okay, if we plug in 0, cosine of 0 is 1, right? And then we go from, let's see here, how can I figure this out or make this easier for us to think about? So cosine of 0 is 1 times 3 is 3, so we start right here, and then we will rotate around, and we'll get back to this point also at pi, right? Because back at pi, we'll be at a negative 1 there, which take us then, or negative 1 times 3 will get you this negative 3. Do we have to use the integral from 0 to pi here? Yeah, we don't have to. So for example, I can also see my circle starts and stops at the pole, right? So I could here, if I wanted to, just say, okay, let's just say 3 cosine theta equals 0, right? Because it starts and stops at the pole, the radius will be 0, so set it equal to 0, and when is cosine of theta equal to 0? It's when theta is pi over 2, comma 3 pi over 2. So alternatively here, you could also use pi over 2 to 3 pi over 2, if that makes more sense about how to find like the starting and stopping point there too. Okay, notice the width of our interval here is pi. The width of the interval here is also pi. Okay, so go ahead, set it up here. All right, from there, I gave you the limits of integration. You guys go from there then. Come up with, you know, your dx d theta and your dy d thetas. Okay. I guess I'll just do it up here. Some of you guys are already ahead, so I'll go ahead and just get to that. Product rule. Okay, what did I mess up? Oh, that's what I missed. Because when you do the derivative of, like this, you're talking,
it's negative.
derivative of cosine to negative sign. Those are hard to remember. We move back and forth from integral to derivatives. Question.
Can you, on the previous problem, what was the answer again?
Previous problem was
Calculator.
5.38828.791.
Good.
Got it? Good. Okay.
Wait, mister, what?
Question.
For this calculator, how do I do sine squared theta?
So you're going to do sine of x,
Okay.
close parenthesis, and then square it. And that should work. If you want to be like extra sure, you can put parentheses around the sine, parentheses around another parenthesis there, and it's x, and then it's squared kind of thing. But that should be okay what you did right there.
Okay.
It won't just square the x because you closed a parenthesis there. So, all right. If you feel good, go ahead and move on to example 13 then. Give that one a try too. All right, give that one a try as well. So, yep. This one they might be a little bit trickier to type in your calculator. But we'll see.
This X, that one,
Yes.
and then Y is that correct?
Should be 2 C's. Oh, sorry. Oh, sorry. Yes. Sorry. I was looking at my dy's, dthetas, dthetas. But yes, what you got right there is good. Yes, exactly right. Yeah, simplify your x and y's on example 13 when you get to that one.
Sine squared of theta.
So x close parentheses squared.
Just squared.
Yeah, just like that. That'll work. If you really want to be sure, Aubrey, you can always put an extra set of parentheses around the sign and then square it too. But that'll be okay, actually, what you have there.
Second squared.
All right, so I'm going to move on here then. Does anyone have any questions on number 12? We're good? All right, so then I'll go on to 13 as well. Yes, derivative tangent is secant squared. I know, it's a lot of derivative and integral rules we have to have down. And sometimes they look very similar to one another. And it makes it hard. Oh, actually, I do want to say a quick note there about number 12. Did anyone do number 12 without calculus?
Oh, you can just take this.
What is that shape? It's a circle. And what is the arc length of the distance around the outside of a circle? Circumference formula. It's 2 pi d. Isn't that really encouraging? Geometry students could have done this. Oh well. Number 13.
If you did that on a test, would it be wrong?
That's a good question. I don't know the answer to that. Because here's the thing I'm thinking about, right? Like if it's a free response question, there might be points associated with like setting up the integral and stuff like that, in which case you would maybe not get those points, but then you would get the answer point because you'd have the right answer kind of thing. So yes, you'd get points if it was a free response, but no, you wouldn't get full points, probably. Secant, remember, is 1 over cosine.
Oh, because it's cosine over
And then they just cancel out. Yeah, isn't that nice?
I mean, I wouldn't mind it. Kind of blows though.
Okay, so I really think the challenge about this problem, because we're given the limits of integration, the derivatives aren't awful, right, when we take them. The really challenge is typing this accurately into your calculator. All right, so I'm going to tell you what the answer is here. Okay. So make sure you can type that accurately into your calculator, because secant is a little bit hard to type into the calculator. All right. I'm going to go over here real quick and draw a graph of this curve, the 2 secant of theta.
I'll go along with it. Because it's I'm so focused on not messing up right now.
You just deleted this word.
Dude, it's work, dude.
No, you already found this. Why put the 0 in there? It's just 0.
Put it in there. Stop judging me.
I won't judge you.
Would secant squared theta be equal to 1 over cosine squared theta?
Yes, exactly right. And that's exactly how you want to do this, because there is no secant button on your calculator.
Finish it. Square that.
You got it correct, guys.
They got it.
And again, this is where I think it's helpful to use that y1 and y2, right? Use the bars, y bars here, because that's, again, that's like a mess to type in your calculator all at the same time. But if you use y, really, I guess all you need, you don't even need y1 and y2, you just need y1, right? Because one of the y's is 0, so you can just kind of ignore it, right? But that's much easier to type into like your y equals first, and then use your bars, y bars function, y1 or something to type in. But that is how you want to type in your calculator. And of course, then it's the quantity squared, I guess. Oh, I guess I'll just finish off the whole thing. Okay, so a better format for writing your calculator is that.
Are you gonna look for that long of a decimal?
No, I give that long of a decimal for kind of like, 2 reasons. One, it kind of eliminates like a rounding error if you happen to round incorrectly, and also 2, if this were like an intermediate calculation, you would want to include like this much precision because you're not allowed to round in between. You want to round only at the end. So now the graph of r equals 2 secant of theta is x equals 2. Remember, right? We found that x was equal to 2, y was equal to 2 tangent of theta. So no matter what theta is, your x value will always be 2. And so it's a vertical line through x equals 2. If we want to find the length of the curve from 0 to pi over 3, well, there's 0. It's this point right here. To pi over 3, that's this point. So it's like this distance right here. That's your angle, pi over 3 right there from the origin, or from the pole. What is this shape? And not only is it a triangle, it's a right triangle, and it's not only just a right triangle, it's a special right triangle. It's a 30, 60, 90 with base of 2, right? And that's the pi over 6 part. That's a small one. So then you double it to get the hypotenuse of 4. And then this is 2 square root of 3, which is the same thing as 3.464101615. So again,
Cool beans, bro.
cool beans. All right, there it is. Questions on any of that?
Exhibit A, like calculus is pointless.
Exhibit A, like calculus is pointless. Just use some geometry. Just use geometry. Okay, so there's that. All right, there's that.
Done.
So you guys, I will stop there. If anyone is interested, I will go through example 9 up here though too. So I'm going to do it for the recording, okay? But you guys can, kind of like, if you want to get started on the assignment, I'll go ahead and post that in the Google Classroom too, maybe real quick, and then I will go through example 9 up here if you're interested. If anyone, okay? So, but otherwise, also the test review will be posted as well here. So.
Lost all respect for it.
Are you kidding me? Okay, Mike.
Mr. Boomer, can I use the bathroom?
Yep.
No.
But don't.
No,
Oh my god.
I don't know. That's like,
No?
dude,
That was mine. Oh my god. It was gonna land. By the way, easy this stuff.
Okay, homework's posted if you're interested in looking at it. I also, of course, have the Chapter 10 test review posted. I would really recommend you get started on that. Tonight's homework is 56, 57, 55, 56, 57, 58. 4 problems. Okay? Tonight's homework is 4 problems. I really recommend you get started on that review. Okay? Is anybody interested in example 9? If so, I suggest you come up here, okay, and I'll just kind of like talk to you all, or I can just talk to myself too, maybe. That would be weird, but I'm going to do it anyway because I want to put it on the video. Okay? Or you can just catch it on the video too, that's fine.
Good morning text.
All right. So let R be the function given by R of theta equals 3 theta sine theta for 0 less than equal to the theta less than equal to 2 pi. Perfect. All right, but you might want to look up there. I don't know if you want to look upside down or something like that. All right, the graph of R in polar coordinates consists of 2 loops as shown in the figure above. Point P is on the graph of R and the y-axis. Find the rate of change of the x-coordinate. You got that? You want to move in? I can zoom in some more too. Find the rate of change of the x-coordinate. So we need to get the x-coordinate in there somehow. How does the x relate to thetas? X equals R cosine theta.
Mr. Wade, can I get a Coach Stein real quick?
So yes, you may. In fact, let me do it down here. X equals R cosine theta. So R is... Thank you. That would have been really bad if I had been doing this for the video and no one could see it. So R is 3 theta sine theta times sine theta. And we want to find the rate of change of the x-coordinates with respect to theta at the point P. Ooh. So we need to figure out what that point P is, or what theta value it is. Okay? What theta? So not pi. Oh, sorry, thank you. I messed up there. Sorry, let me fix that. Thank you. Okay, so where is P on our polar graph? It could be pi over 2, or we could be 3 pi over 2, potentially, if we had a negative r value. So we want to be careful. Which one is it? Well, we can use our graphing calculators to help us figure out what it is, because we do have the capability of using that. So let's just do that.
Oh, yeah. One of those little car keys.
So 3 theta sine theta, Mr. Wig. Graph it. Whoops. Zoom 6 and zoom 4. Nope. Zoom 6 is what I want. Okay. So that's P right there. So if I do second trace, I can type in value, and I'm just going to guess pi over 2 and see if it works. And pi over 2 is the location of that point. So that's good. We want to evaluate then the derivative of this dx d theta at theta equals pi over 2. So we got to find the derivative of this, right? No, our calculator does derivatives for us. So let's use the calculator to do that. All right? So we're going to do dx d theta here, which we can't use that, but we can do change our mode back to function, math 8, and we'll take the derivative with respect to, we're going to use x's in this case if that's okay. 3x sine x cosine x, evaluated at pi over 2. And we get approximately negative 4.7123, so. Okay. Negative 4.7, which indicates what is happening here. If the rate of change of x with respect to theta is negative, that means our x values are moving which direction? Left, right? Because our x values move left, right. Which makes sense because if we go back to the graph, whoops, let me go back to polar mode here. We can see that at that pi over 2, we are in fact moving left, right? We move to the left at this point. We're moving left to continue the graph. Okay? Letter B, find the area of the region between the inner and outer loops of the graph. So that's this. Okay? This is a scenario where we want to subtract. We're going to subtract here. Okay?
So you get everything you learned?
Okay? It's the outer curve. The outer curve here, well, it's when the pole equals 0, right? So, or when our curve equals 0. Or we can use our graphing calculators, I guess. That's easier, too.
That would be so funny.
So if I just trace it here, starting at theta equals 0, we start right there, and I trace it. Go around, do. And it looks like at pi, we're back at the pole. And so it's at pi when our big curve starts, and we trace around there. back around to the 0 at 2 pi. So our outer curve is from pi to 2 pi. And I'm just going to use r of theta there to represent our outer curve. Squared d theta minus our inner curve. But our inner curve, what are the limits of integration for the inner curve? 0 to pi. And again, r of theta squared d theta. So there is our setup. Okay. Can we utilize symmetry in this situation? No, we have no symmetry, so you have to set up without symmetry.
Actually, you non-nerd.
Okay, if you calculate that, you should get something like 139.5282451. Okay?
I didn't do it.
All right, and I'll stop the video there.
All of the week, or don't do any of it.
How many questions and tests?
Okay.